Thank you everyone for being here. I'm Rachel Harkness. I'm the programming manager at the Portland Public Library, and we're thrilled to be partnering with the Camden Conference once again on their community event series. Firooza Pavri is here with us today, and I'll let Betsy Mayberry from the Camden Conference introduce her in just a minute. So I hope you all enjoy the talk, and I'll hand it over to Betsy Mayberry to introduce Firooza.
Hello, I want to welcome you as well. I'm going to talk a little bit about the conference before I introduce Firooza. Our 34th annual Camden Conference, the Geopolitics of the Arctic, a Region in Peril, was held on the 20th and 21st of February, last weekend. We had a terrific roster of speakers, beginning with our keynote speaker, Hofsjökull Grimsson, the former president of Iceland, and a large number of attendees, over 1,500, all virtual, from 12 time zones across the globe. So we said good morning, good afternoon, and good evening when we welcomed people to the conference. I want you to know that this conference will be on the Camden Conference website in 2 weeks, camdenconference.org. So if you didn't have a chance to go to the community events and didn't have a chance to go to the conference, here's your opportunity to become a new expert on the Arctic. I want to introduce Firooza Pavri today, who is our guest speaker. Firooza is director of the Muskie School of Public Service at USM and is a professor of geography there. Prior to joining USM, she lived in the Midwest, receiving her MA in Geography and Planning at the University of Toledo and her Ph.D. in Geography at Ohio State University. Originally from India, research and family take her back there frequently. Her teaching and research are in the area of environmental geography with a focus on society-environment interactions, natural resource conservation and policy, sustainable development, and geospatial technologies, including satellite imaging. More recently, her work has focused on subarctic environments in Iceland and Southern Greenland. This is the topic she will be sharing with us today. I give you Firooza Pavri, who will speak about changes in subarctic Iceland and Greenland. Firooza.
Well, thank you so much, Betsy and Rachel. I'm really pleased to be here, and thanks for the invitation. I'm so glad to share some of this research with our viewers. So I will actually just share my screen since I have a PowerPoint. Well, thanks again, Betsy, for that kind introduction. I'm going to talk a little bit about some of my recent research in the Arctic, both in Iceland and Greenland. But before I start, I just want to acknowledge two of my students who have been alongside me on this journey, Diana Farrell and Isaac Onos. They are both students at the Muskie School of Public Service. And I have to say, one of the joys of being a faculty member and a teacher at a university is that you get to work with brilliant students. And these two students have really done some amazing work. So I want to acknowledge their role in these projects. And of course, also the funding that comes from the Maine Economic Improvement Fund at the University of Southern Maine, and as well, the University of Maine Arctic Futures Institute that sponsored a faculty exploration trip to South Greenland. So if you have been attending the Camden Conference on the Arctic, or you're interested in the Arctic, then you know that there are some significant changes going on. And I think this map sort of encapsulates what's been going on across the globe, not just the Arctic, across the globe, and the fact that scientists are paying attention to what's going on, and of course the public as well. So what this map shows us is temperature anomaly from a long-term mean or average between 1951 and 1980. And it shows you those regions that see temperatures that are above the long-term average and those that might be below that long-term average. And the one striking thing about this map, I think, is number one, the Arctic stands out. I mean, clearly, what we've been hearing in recent decades is, of course, something that we've been calling Arctic amplification. The fact that temperatures are increasing here across the Arctic at a greater magnitude than we see elsewhere across the world. So the Arctic is certainly a region that has drawn tremendous attention from scientists across the globe. The other thing that's actually interesting about this map is that if you look across the Arctic, it's not the entire Arctic region that is changing simultaneously and kind of to the same extent. I will be talking about two areas, one in the country of Iceland, and then the second one from South Greenland. And what we find is that if you look at the Arctic region, you know, the temperatures have increased to a far greater extent across Alaska, northern Canada, and of course, northern Siberia, and perhaps to a lesser extent in the southern part of Greenland and across Iceland. So that's something just to keep in mind. Nonetheless, we recognize that this change is occurring globally. So what am I going to talk about today? I'm going to share with you a particular vantage point for looking at landscapes that undergo change. I've always been fascinated by how landscapes change over time, whether that's natural change or anthropogenically induced change. And something that I've used throughout my career has been satellite data. Satellites have been around for 50 years now. They've been collecting systematic data for the globe right through this period, and they've provided us with a repository of tremendously valuable information, and particularly relevant to the Arctic and polar regions. And why the Arctic and polar? Because they're difficult regions to study. The environment is harsh, it's cold, it's difficult to access. And so the explorers and the scientists who went to the Arctic and the Antarctic to collect data, they were, you know, pretty strong, intrepid folks that did amazing field work. With satellite data, however, a lot of the field work can now be data that's collected through these satellites. So I'll be talking about what the satellites tell us about the changing conditions across Iceland and Greenland. You can think of these satellites and their sensors as space-based observatories. That's the way I think of them. They really provide a view of the Earth's surface from a very unique perspective. It's like looking out of an airplane window and looking straight down. That's what the sensors are doing. They're gathering data that's not readily available to us. The sensors are gathering data about the atmosphere, its composition, about gases, about particulate matter, about temperature conditions. And of course, they're also gathering data about the Earth's surface itself. There is a temporal frequency that's unparalleled. These sensors are continually orbiting the Earth, and they will keep orbiting until they sort of live their life and break down. So we've got this unparalleled data set, in some cases going back, 30 years, 30 plus years, and in other cases to a shorter extent. And the other unique thing about these space-based observatories is that they've expanded our view of the Earth. They're gathering data not just in the visible part of the spectrum, that which we can see with our eyes, but also in the infrared part of the spectrum, in the microwave regions, etc. And those are areas that actually give us a tremendous amount of information about the Earth's surface. So we'll be looking at the infrared part of the spectrum today. And of course, you have this fantastic historical archive. So let's start with the first case study that I wanted to talk about today, and that's Iceland, central Iceland in particular, and the ice cap of Hofsjökull. If anyone's been to Iceland, you know it's an amazingly beautiful country. The geography is quite spectacular. It's known as the land of ice and fire, and with good reason. You have Vatnajökull, which you can see on this map, which is the largest ice cap in Europe outside of course, the Greenland ice cap. And you've got other smaller ice caps as well across this wonderful country. But of course, what you also have is it's a volcanically active zone. It sits right on the North Atlantic ridge zone. And so you've got a lot of volcanic activity that's going on in different parts of the country. We chose, this is my student, Diana Farrell, and I were working on this project, and we chose Hofsjökull for a couple of reasons. It's in the central highlands. It's not a populated region at all. It's been sort of overlooked, primarily because the other coastal ice caps have drawn a lot of attention in Iceland. Particularly, you might remember Eyjafjallajökull, kind of a tongue-twisting name, but nonetheless, this is the ice cap that's responsible for shutting down air traffic over Europe in around 2010 when it erupted. So we've decided we're working with Hofsjökull, and we use a particular sensor called Landsat, which you may have heard of. It's a NASA sensor. There have been several iterations of Landsat, with Landsat 1 going back into the 70s. And then we have currently Landsat 8, which really extends the sort of time scale of data that we can get from the Landsat sensors. So how does Landsat help us? Well, a variety of different ways. Landsat data is what we call moderate resolution. How crisp is your image when you look at it? Well, to the lay public, it might seem like, not very useful. However, to a trained analyst, moderate resolution data can provide a tremendous amount of information. And we'll see a couple of examples. It has a long historical archive, so it allowed us to go back in time to look at changes across the Hofs ice cap. We used the images not only in the visible part of the spectrum, but we found that the near infrared bands were particularly useful to us when we were looking at ice cover and also when we were looking at vegetation. Landsat is readily available. It's free to download. It's updated regularly. And so it was extremely appropriate for the analysis that we were conducting. And what we really wanted to do was get a sense of where and how quickly the landscape across the Hofsjökull region was changing. We knew it was changing. The temperatures have been increasing. There have been other shifts as well. And so we wanted to monitor what was going on. So before we get to a space-based image, I thought it would be kind of nice to look at the area from the ground. And so here are some photographs of the Hofsjökull ice cap that you can see in the background there. In the foreground, you see this kind of absolutely treeless plain. It's classic tundra. You can see mosses and lichens and small shrubs, maybe a few stunted willow off and on, but it's really a tundra landscape. And here on the bottom of the image, what you see is rhyolite mountains. If you're looking at this image, Diana is standing in these mountainous areas. She's in the mountainous areas while she took the image of Hofsjökull in the background there. So really fascinating landscape. Hofsjökull actually sits on top of a dormant volcano, a caldera, that's about 600 meters deep. It has not erupted in quite a while, but of course that's not to say it wouldn't in the future. The heat from the vent of the volcano below the ice cap does contribute to some of the melting of the ice cap as well. If you look at some other images from the region, you see once again some of the outlet glaciers that make their way down from the ice cap itself. They're really quite remarkable. On the ice cap, you'll see a lot of debris, ash, that could have been blown over through other eruptions that may be occurring elsewhere in Iceland. It could be debris from the ice cap itself, rock, mud, materials like that. And then you see these moraines here that carry down a lot of the debris from the center of the ice sheet down into the edges. And what you see here on the right is really sort of the vegetation right? Now, this is a September image, so things have already senesced, but you can get a feel for the vegetation. There's really low to the ground, a lot of mosses and lichens and those sorts of things. And then you will see occasional flowering plants, etc. And especially when you get to bodies of water, you will see sedges, some grasses, etc. So here we go from the ground to space, right? And these are two images of Hofsjökull. The left image is from 1992, the right image is from 2017. These are Landsat images in the near infrared band. And the one thing to know about near infrared images is that it's not what our eyes can see. We can only see in the visible part of the spectrum. But what we've been able to do with our software and with image techniques is we build what we call false color composites. False color because we have given a color to the near infrared band so that we are able to see the data that's being gathered in the near infrared part of the spectrum. And so really the thing to understand here is that the red tones that you see is really referring to vegetation, okay? You see the ice cap very, very clearly. Title B here and here. This is the Kerlinga Mountains, the one where Diana was standing to take images of the ice cap itself. And you can see some really distinct changes across the 25-year period. The ice cap itself, you see, especially on the edges, is going through breakup. You see a lot more debris on the surface. You see a lot of the moraines that are carrying down materials, etc. And some of the really interesting features that we were focused on is, for instance, this outlet glacier is extremely famous all across the globe, especially with geologists, right? It's the Hofsjökull outlet glacier, and it's famous because it has gone through periods of retraction and then expansion over the past few decades. Currently, it's in a retraction phase, but right at the edge of the Hofsjökull is an active drumlin field, and a drumlin is a feature of glacial landscapes. It's one of the only known actively building drumlin fields in the world today, and so geologists flock to understand how that works in this region. And then one other area that I want to point out to, this area that you see in particular, which is very, very bright red, less so perhaps in the earlier image, is a very famous wetland. This is a tundra meadow wetland called the Torsever, and the Torsever is famous because it has been designated by the Ramsar Convention on Wetlands as a wetland of international importance, primarily because of the bird life that it supports, but also because of the biodiversity it supports in this kind of tundra landscape. So what we started doing is started analyzing these images, and then we looked at them in greater detail, and we do a lot of quantitative analysis. But what we come up with, really what our intent is, to look at the big categories of landscape that we see here. We were interested in the ice cap and how that was shifting and changing. And so we create these, what we call classified images, that really quantify what's going on the ice cap, but also quantify some of the vegetation changes that we're seeing. And our study found that between that approximately 25-year period, we saw a dramatic increase in Arctic vegetation in this region. So as it warms, of course, vegetation not only needs warmer temperature, but it also needs other conditions, soil conditions, water availability, nutrients, etc. But it seems like Arctic vegetation is expanding across the region. And the other thing, of course, we noticed is that there has been approximately a 23% decrease in snow and ice cover across the region. So while Hofsjökull isn't going to disappear anytime soon, not for quite a few decades, if current temperature trends keep at the same sort of warming phase. Nonetheless, it's an area that's important to pay attention to, because you've got the wetlands of importance, international importance here, but also you have a river here that has its origins in Hofsjökull that supplies a lot of the hydroelectricity that is used across southern Iceland. So there are certain interesting sort of, you can imagine that there will be consequences in different areas, both for the vegetation, perhaps for human habitation, etc., if the trend for retreat of the ice cap continues. What we also did is look at, I talked about the quantification of the changes that we're seeing in the ice cap, and that's something else we were able to do. So we can actually map out where is the ice cap shrinking, where is it retreating, how much is it retreating, etc. And the maximum that we found was that the ice cap in certain areas had retreated 1 kilometer from its 1992 margin. So these data give us all sorts of information that would be very, very difficult to gather otherwise. Of course, you could have field surveys, which were done in Iceland with fair regularity, but this makes it so much easier. And what it also does is it enables you to keep monitoring these regions into the future. So just kind of a quick recap of the Iceland study. These frequent assessments can provide us with an enhanced understanding of what's going on. The methodology that we used is robust. It's been used widely. It reduces errors rather than having someone hand trace or hand digitize the ice cap. We can use something that's much more automated. And it will be useful for other regions of the Arctic as well, other hard to reach regions of the Arctic. And as a future study, we're considering perhaps looking at the Thorsaver wetlands that I mentioned earlier for closer analysis and study. I've always been very interested in wetlands. I've done a lot of research in wetland environments. And so what I would be really interested in looking at is how are they changing? Wetlands are a feature across the Arctic, and they're going to go through tremendous change as temperatures warm. So what is going to happen to these wetlands? How are they going to change? I think more needs to be done so we understand them thoroughly. And so that's perhaps a future study that I might undertake. So then we fly about 1,200 kilometers to the west to come into South Greenland. And the South Greenland study that we've started is relatively new. I had the opportunity to visit South Greenland with a team of faculty from the University of Maine Climate Change Institute and University of Southern Maine. And we're looking for opportunities for research. The Climate Change Institute has worked in Greenland over the last 40 years. So they have a long, tremendous record of scientific work in Greenland. And we visited in particular the southernmost sort of tip of Greenland, South Greenland, and you can see it blown up here in an image, is really quite amazing. If you know something about Norse Viking history, then we know that this area of South Greenland was settled by the Norse Vikings during the medieval period, starting around the late 900 ADs and into about the mid 1300 ADs. They had two settlements, the Eastern settlement spread out across this region, and then the Western settlement, which was some ways up the Western coast. They survived for about 300 odd years, did quite well, farmed, etc. But then the civilization died out, and it's been one of the mysteries in the scientific world as to why that civilization died out. Of course, we know now that one of the reasons perhaps was climate change. It suddenly cooled, where the Norse could no longer engage in farming. And perhaps that's one of the reasons why their civilization was wiped out from here. Nonetheless, we visited this region of South Greenland. There are communities spread out across this fjord region. We visited a few of these communities. You have, for instance, still archaeological sites that have been dug up and preserved. This, of course, is a very famous site, the Valsay, which is ruins of a church from that Norse Viking period. It really is quite astonishing to land and walk around it. You also have other sites that have been excavated. For instance, this is a farming community in Igaliku. On the top left, you see some of the excavations and the archaeological sites where they've been able to find the stone building materials that were typically used by the Norse. They would build with stone and have roofs that were thatched to preserve heat. And then you see Igaliku today, and it is a farming community with sheep farms, etc. So what were we interested in? And in this study, of course, we have two of my students, Diana Farrell and Isaac Onos from the Muskie School, who have been helping with this study. So what we were looking at, and what we are looking at across South Greenland, is really understanding seasonal and decadal shifts in vegetation cover. As this region warms yet again, what kinds of shifts will we see in the vegetation across the area? I think I failed to mention this earlier, but this region of South Greenland called Kujataa is also now a UNESCO World Heritage Site. So it is a region of global importance. What we're doing is mapping the variability, both spatially, geographically, and temporally, and monitoring this coastal fjord landscape and the terrestrial greening or browning patterns that we might see. So it's interesting. The scientific literature has indicated that as the Arctic warms, there is the tendency, of course, you would think, for the Arctic to become greener. So as it warms, there's more vegetation that will come up. However, what our mostly satellite data have shown us is that the greening is not universal across the Arctic. There are many areas of the Arctic, both in Alaska and then parts of Siberia, of Western Siberia in particularly, that are not greening, but what we call browning, quote unquote. And essentially that the water conditions perhaps might not be ideal, or the soil conditions may not be ideal for vegetation to expand in those areas. And of course, one of the things that I am fascinated about is understanding the human impacts from this landscape change. So as this area perhaps warms, what is the impact on the farmers that live in South Greenland today? Sheep farming is very, very common in South Greenland. So what is the impact on those farmers? Well, let's look at an image. Now you're used to looking at Landsat and a near-infrared image, and you know that the red tones indicate vegetation, but also look at this vast ice cap in the background there. In the foreground, you see the glaciers coming out, meeting the ocean, and you see this very typical fjord landscape. Here is that same map that you saw earlier. You know that the communities of South Greenland are spread across this fjord landscape. So if we come closer to Earth from our space-based images, then the top image that you see here is from an airplane where we're just landing in South Greenland. And you can see just the vastness of the ice cap beyond. This is pointing north pretty much, and all you see is ice cap all the way to the horizon. But when you get to the ground, and especially in the coastal areas, we're seeing a lot of the coastal glaciers that come meet the ocean. And we're also noticing and observing when we're in the field, the retreat of these coastal glaciers. To give you a sense of scale here, if you look really closely, there are a few people down here in that image. These glaciers, that wall right there seemed like at least 100 feet or so, if not more. So really stark but beautiful landscape. And when you are close to the ice cap and the glaciers themselves, the vegetation is quite typically Arctic tundra vegetation, short, close to the ground, few flowering plants, maybe willows, etc., short stunted willows and whatnot. And of course, tourism is taking over this region as well. So you see a lot of, well, not a lot, but you do see a steady stream of tourists coming into South Greenland. The vegetation pretty much latches on to any nook and cranny that it can find. So on a steep slope, steep hillside, you can see vegetation in the crags and the crannies, and that's fairly typical. So what you see is this kind of gradation is what I'm trying to get at. Close to the glaciers, you have tundra vegetation. As you get farther away, the vegetation somewhat changes, becomes denser. You have taller trees. These are willows, birches, etc. You have a fairly significant vegetation cover in the sheltered fjords. They're sheltered from the winds and the storms and whatnot. And then, of course, in the valley, in the fjord valleys, you have these tremendous meadows. And these meadows are where most of the South Greenland sheep farming occurs today. And so we had the opportunity to visit quite a few sheep farms as well. So in the South Greenland study, we take a different avenue. We don't use Landsat, but we use another data sensor, MODIS. MODIS is another NASA product. It's moderate resolution. Landsat is 30-meter resolution for each little pixel that you see on a Landsat image. That's 30 meters by 30 meters. MODIS is 250 meters, so it's slightly coarser. Nonetheless, for the big region that we're looking at, for the vegetation analysis we're conducting, MODIS is perfect. What MODIS allows us to do is build a so-called vegetation index using the different bands that it captures. And this vegetation index tells us a little bit about where greening is occurring, but also the vigor of the vegetation itself. And MODIS provides images on 16-day average data. And so we collected this data from 2000 to 2020. That's 20 years of data for the months between May and September. And we currently have over 200 image sets, which we are slowly making our way through. And what I am going to share with you is just a few snapshots within that larger 200 data image set. But one thing to keep in mind, when we're looking at remote sensing analysis, satellite image analysis, we always want to keep in mind ancillary data. Ancillary data, anything that can help us explain what's going on within these images. And so we wanted to look at temperature anomalies. What is going on in terms of temperature changes across this 20-year period? And we actually look at a far longer time scale. But for now, we'll just focus on the 20 years that the study is over. And, you have temperatures that range above the long-term average or below. Here's the average, the long-term average. And so what you can see is most of the temperatures, both the blue, which is the wintertime temperatures, and the orange, which is the summertime temperatures, for the most part are above the long-term average, with a few areas where it does dip below. Now, what I'm going to show you are 3 time slices: 2000, 2010, when temperatures were quite above the long-term average, and then 2020, just last year. So kind of keep in mind that there will be a lot of variability in between, but let's for now just look at 3 time slices. So here's the area from MODIS, right? And what we've done is built a vegetation index. The darker the green, the more vigorous the vegetation is how you would interpret this image. And the yellows would indicate very, very minimal vegetation and perhaps, in some cases, bare ground. So you have May 2000, July 2000, September 2000. Very typical growing season. Early season May image, very little vegetation showing. The peak of the growing season, yes, a lot of dense vegetation that we can see, a lot of vigor. And then as the vegetation senesces, it turns fall, it's dying out slowly. We see this for 2000, 2010, and 2020. So now we can sort of start building our story, right? What is going on in these 3 years? Particularly look at May and then look at September. May in 2000, very minimal. In 2010, quite significant. And in 2020, perhaps scaled back again. So we do know that 2010 was an unusually warm year. Even the winter prior to 2010 summer was unusually warm. Certainly explains what's going on in this series of images, right? But really the study is ongoing. So we're going to have to look in between that entire decade to see what exactly was going on here. Another way to look at it is we're going to be looking at those seasonal trends, right? So now we just have the May images side by side, May 2000, 2010, 2020. And so you can really start doing that comparative quantitative analysis to see a couple of things. I'm really interested to see how far up into the glaciers and ice caps do you start seeing a vegetation signal? Secondly, I want to know how early is vegetation starting to show up in our imagery? So in other words, is the season getting earlier and ending later during the year? And then there's a host of other questions that we will be asking these data. So this is the May image from all 3 years. Here's your July image, the peak of greenness as we know it. Clearly, you can see some very interesting greenness trends, most recently from 2010, as opposed to earlier years. And then here is when the vegetation senesces, or in September, where things are starting to scale back and go dormant for winter. So this is an ongoing study. We still have a lot of work to do, and I'm going to be excited, and I know my students are very excited to see how this all turns out. I know I'm sort of running out of time, so I just wanted to throw together some conclusions, concluding thoughts and future steps, right? I think space-based imaging has really revolutionized how we monitor Earth, how we understand what's going on within our systems, and how we think about change as well. It is unparalleled in the amount of information it has provided. I'm very interested in how these changing conditions, whether they're naturally occurring or whether they're human-induced or anthropogenic, how are they affecting landscapes? And not only the landscape, but how do they affect the community that lives there? For instance, the sheep farmers in South Greenland. And how does it affect their livelihood? When we spoke to the sheep farmers, they talked about change. They could see it happening in front of their own eyes, and it wasn't all good. So how do we understand that using these data? And then monitoring these changes, I think, helps communities anticipate perhaps what might be to come. It helps them prepare for the implications of change, and perhaps would enable them to reduce their risk and build their resilience to climate change. So that, in a nutshell, are the 2 projects that I've been working on with my students in the Arctic. But I just want to leave you with, hopefully this will work, just 10 seconds of a video clip that is taken in 2019, June of 2019, at one of the outlet glaciers in South Greenland. And you can see the force with which the glacier melt is coming out. And this is just one of thousands of outlets where meltwater is coming out of the Greenland ice cap. Later, of course, we learned that 2019 was a year that saw the most dramatic melting of the Greenland ice cap. So this gives you a sense of being there and seeing the kinds of things that we saw. And I'll stop that there, and thank you very much. And I'm glad to take any questions.
Thank you so much, Firooza. That was really, really interesting. And we do have a couple of questions. So Firooza, Bill asks, is the spread of vegetation by natural seeding, and how are the seeds moved?
Yes, it is all natural seeding in both the instances. So most of it is, I would say, windblown. Some of it might be, moved with water, but most of it would be wind-driven seeding of vegetation in both those areas. And the winds can be quite fierce in both regions.
Jean asks, you have talked about temperature in Greenland. What about rainfall, and what about drought?
Great question. Yes, so I have not shared the precipitation trends, but what we are doing is studying those really carefully, because one of the concerns, especially in South Greenland, is that the rainfall is not quite as as it used to be. So it's actually declined. That's some of the anecdotal evidence that we got from a lot of the farmers are finding that in the last 10 to 15 years, they've seen a decline in precipitation, which of course will affect the vegetation growth, and that in turn will affect their sheep flock. And so a couple of the farming communities that we visited had reported that certain years their flock is greatly diminished because of reduced precipitation trends the year before, et cetera. So that's certainly something that we're going to look at very carefully.
Thank you. Grant asks, browning versus greening was mentioned in respect to certain regions. Are there hypotheses for what causes these different vegetal responses to warming?
Yeah, absolutely. So there's all sorts of conditions that are required for vegetation to take hold. Everything from temperature, precipitation, nutrient availability, soil conditions, what kind of wildlife there is around, etc. And so in the areas where there has been enhanced greening, the trend seems to suggest there's also been ample precipitation. In the areas that are browning, those are areas that have seen perhaps reduced or more sporadic precipitation, kind of not necessarily the typical kind of precipitation pattern that they would have received, but that things are changing somewhat with their precipitation patterns in those browning areas. There are some really interesting studies that have been done globally to look at the Arctic and look at greening and browning trends, and they're quite remarkable when you look at where these trends are occurring. Alaska, interestingly enough, is seeing quite a bit of the browning trend, as I had mentioned, I believe, Western Siberia, parts of Western Siberia, etc. Some areas are just, they are as you would see them over the past few decades. So there have not been many changes, but then there are others where there's greater greening or greater browning.
Okay, so Kathy asks, is there permafrost in both of these regions, and did you look at how it's changing? Why is the Arctic region warming so much faster than the rest of the Earth, and why does the Antarctic have the least amount of warming?
Okay, many questions there, which I'm not sure I'll be able to fully answer all of them. I'm certainly not a climatologist. But so the first question was about permafrost, and no, there is no permafrost necessarily in the Icelandic context or in the South Greenland context where we were working, right? Of course, if you go a little ways away, you will encounter permafrost. And of course, we found lots and lots of other studies that suggest that permafrost is melting quite rapidly, parts of Alaska and all across Siberia as well. Siberia is actually facing some tremendous issues with permafrost melt. It has affected some of their hunting and nomadic communities. It has also affected a lot of the gas and oil industry that's all across parts of Western Siberia, et cetera. So permafrost is melting, not particularly to my study. It wasn't that big of an issue. The other question was the enhanced effect in the Arctic. And there's several reasons for this. Some have to do with wind patterns and how winds carry how the temperature, how the warmth is distributed across the globe. So warming from the tropics and the equatorial regions that reach into the Arctic areas. The warming is also in a way enhanced because of water in the Arctic. Now that water was typically ice covered, and you have this huge Arctic, ocean ice or sea ice that is melting. And as the ocean sea ice melts, it reveals dark areas of water. And this water has the ability to trap heat. And so that enhances the melting itself. And so it's sort of this domino effect. So I probably haven't explained that very well, but it's outside of my sort of area of expertise. But there's a lot of literature on why the Arctic in particular.
Okay. And then Zuzi asks, how do we distinguish the melting that is caused by the volcanic activity that takes place underneath the Icelandic ice caps versus global warming that affects the ice sheet from the surface?
Yes, good question. So that the warming is happening from below. So it's at the bottom of the ice sheet that's experiencing the warming, and it could be causing melting there. But because of this tremendously large ice cap that's sitting on top of this caldera, and the caldera is not really quite that active at all, that keeps the ice cap intact and it's relatively stable. Of course, there are periods when there will be enhanced melting, perhaps if the volcanic vent gets a little more active. But most of the melting that studies have found has been occurring on the surface of the ice cap. They measure how thick the ice cap is and how much that thickness changes over time. And so most of the studies have been focused on the surface melting that's going on, which is because of, temperature changes perhaps in the atmosphere.
Thanks, Firooza. We just have a couple of follow-up questions. Bill asks, in regard to the seed types, have the plants evolved as wind-dispersed seed types?
That's a good question. I have not seen any literature to that effect, any long-term studies. I mean, certainly there will be an evolution of what types of plants you're seeing in these different areas if the warming trends continue, right? So if warming continues, certainly we're going to see variability in the vegetation. So we'll have different compositions, plants, et cetera, that we'll see. So that's certainly possible, but I haven't really looked into that in much detail.
And Jean asks, is anyone monitoring soil changes, acidification, invertebrate, soil temperature, etc.?
There are other scientific groups, both in Iceland and in Greenland, that are doing those studies. And I haven't interacted with those groups, but I do know that they are there monitoring all of those conditions.
I think that was it. That was a good set of questions. So I just wanted to say thank you again, Firooza, for supporting the library and doing this event. We had a great audience, and thank you to the Camden Conference for making these available. Sorry, I'm just looking. There is one more question, and then we can say goodbye. Do you include any First Nations in your studies?
Great question. So we haven't gotten to the part where we're really actively engaging with the groups that live there currently. We're still in the phase of monitoring the landscape and looking at what kinds of changes are going on. I talked about anecdotal evidence from visiting farms and that sort of thing. So that was all sort of as part of one field trip, but we haven't started anything systematically, although the plan is to do so, which is to systematically talk to different groups, the First Nation, the Inuit groups. And of course, the Greenlanders are quite interesting because they don't distinguish themselves. They call themselves Greenlanders, and they're very proud of that. But we will be talking to different farming communities across South Greenland.
All right, thanks for sneaking that last one in. All right, well, thanks again, Firooza. Thank you to the Camden Conference, and thanks to everyone that made time today to see the lecture.
It was a wonderful event.
Thank you so much. Thank you so much for having me. I've enjoyed it.
Bye.
Bye-bye.
Bye-bye.
Thank you all. That was fascinating.